Next, we move on to example 43. This is another example of computing expectations for a continuous random variable. So let x be a continuous random variable with PDF of the following form. For values of x between 0 and 1, the expression for the PDF is 4x minus 4x cubed. For any other value of x, the PDF evaluates to 0. And so again, we have seen this example before. We've seen this PDF before, this distribution before. And so we're going to continue looking at this distribution by computing the mean of the distribution, in other words, the expected value of x, the variance and the standard deviation of the distribution, as well as the skewness and the kurtosis. All right, so by definition, the expected value of x is equal to the integral over the real line of x times the PDF. And again, since the sample space for this distribution is the unit interval from 0 to 1, this integral simplifies to the integral over the unit interval from 0 to 1 of x times the expression for the PDF over that interval, which is 4x minus 4x cubed. So using properties of integrals, we will decompose this integral into a difference between two integrals. So we first distribute the x across this expression here inside the parentheses, and then use properties of integrals which allow us to re-express or rewrite an integral of a difference in terms of the difference of the integrals. We also use the fundamental theorem of calculus, right, to calculate the resulting integrals by finding the antiderivative of each, and then evaluating those antiderivatives at the upper and lower endpoints of integration, and then taking the difference. And so when we go through these calculations, we see that the mean of this distribution, the expected value of x, is 8 over 15. To find the expected value of x squared, again, we calculate the integral of x squared times the PDF. All right, and you can see these calculations. I'm not going to read them off, but when you go through this, the second raw moment, the expected value of x squared, is found to be 1/3. Now, with the first two raw moments, we have all we need to calculate the variance of the distribution using the expansion formula. Right? So the variance of x is given by the expected value of x squared minus the square of the expected value of x. So 1/3 minus the square of 8/15. And when we go through and do a little bit of algebra, we get the value 11 over 225 for the variance. Okay, next we find the third raw moment, because again we're going to use the expansion formula to find the third central moment. So we'll need the third raw moment first. And so again, you can see here the calculations. We're just continuing on as we have. And so if you're doing these calculations, and I would suggest that you do them, so just take out some paper and redo these calculations on your own, and then compare your work with the results that we get here on the slides. And so then it'll give you plenty of practice, I think, to get you back up to speed on some of this basic calculus that we need for the course. So going through this process, we find that the third raw moment, the expected value of x cubed, is 8 over 35. And now we have the first three raw moments, and so we can use the expansion formula to compute the third central moment. All right, and this turns out to be given by, let's see here, so representing this as a decimal approximation, negative 0.001354. Now we have the third central moment. We also have the variance, and so we can calculate the skewness coefficient by dividing the third central moment by the variance raised to the third 3/2 power. And so when we do that, we get a value of negative 0.1253 rounded. So this is the skewness coefficient rounded to 4 decimal places. And then finally, we'll find the fourth raw moment. after which we'll use the expansion formula to find the fourth central moment on our way to finding the kurtosis of the distribution. So again, doing these calculations, as you're now, I'm sure, becoming very familiar with, as well as the definitions for these various moments. So we find that the fourth raw moment is 1/6. Okay, and so now that we have all first four raw moments, we can utilize the expansion formula to find the fourth central moment. And so plugging those values in and just being very careful in our calculations, we get a value written as a decimal, 3693 over 708,750, or expressed as a decimal approximation, positive 0.005211. And so then, once we have that, we can use it to find the kurtosis. We divide that value by the square of the variance. So the variance was 11 over 225. We square that, and we get a value of 2.18 for the kurtosis of this distribution. All right, so let's look at see how to do this with the calculator. And so again, the first thing I will do is to calculate the mean of the distribution. So we press the math button, select the numeric integration function. We enter the lower and upper endpoints of integration, 0 and 1 respectively. All right, so we're going to find the mean. So that's the expected value of x times the PDF. And so over the unit interval, the PDF is 4x minus 4x cubed. Now notice that I did not have to put the multiplication symbol in between the 4 and the x. Okay, I was doing that before just for the sake of completeness, but you actually don't need to do that. Okay, so there we go. I got to get the parentheses in the right spot. Okay, and so that looks like that's formatted correctly. And so let me try. Okay, yeah, so that worked out. And let's see, we can convert that to a fraction. And so the mean of the distribution is 8 over 15. Okay, now we're going to calculate the variance via the definitional formula as the second central moment. And so I'm going to select the integration function. And I need to put in some extra parentheses here. So let's see, we have x minus the mean, which I will grab by highlighting. Okay, and then we square that. And then we need to enter the expression for the PDF, which is 4x minus 4x cubed. Okay, and then I need again to close off that parenthesis. Okay, that looks like it's formatted correctly. Be sure to enter the variable of integration there. All right, let's give it a try. Okay. We change that to a fraction, 11 over 225. All right, so now let's continue on. Let's find the third central moment so that we can then find the skewness. And change that to 3. Okay, let's see if that will convert to, okay, so that doesn't have enough precision to calculate it to convert that to a fraction. Okay, so to compute the skewness coefficient, we select the third central moment. We divide that by the square of the variance. I'm sorry, the variance raised to the 3/2 power. Okay, so, oops, well, I messed that up, didn't I? So let me go ahead and let me get back here. Let me just clear the whole thing. Okay, we grab the third central moment, divide that by, and then we go up again and grab the variance. We need to raise that to the 3/2 power. And so that's what we get. Negative 0.12530 rounded to 5 decimal places. And then to calculate the kurtosis, we will need the fourth central moment, which we can again calculate directly using this calculator. And let me see here. Okay, again, does not have quite enough precision to convert that to a fraction, but no worries. We'll divide that by the square of the variance. So we get 2.1800, rounded 4 decimal places. All right, so that's how you can do the calculations for this example on the TI-84. You can also do it on the TI-36X Pro, several Casio calculators, HP calculators, and so forth. Okay, so I want to continue talking about some special expectations. So consider the function defined by this expectation. The expected value of e raised to the tx power, or equivalently, as I've got it typed in here, the expected value of the exponential function evaluated at t times x. Now, if this expectation exists for every t in some interval about 0, then we call this function the moment generating function, and we'll denote it this way. Cap m sub x, so m is for obviously for moment generating function, then we'll indicate the random variable down here. You don't have to, but if we want to make sure that we understand which distribution and which random variable we're talking about, that's good practice. All right, and so the moment generating function is defined to be this special expectation, and the moment generating function for a distribution exists only if there is some small interval around 0, or some interval around 0, no matter how small, for which this expectation exists for every t in that interval. Now, the moment generating function is useful for several reasons. The first is that it's used for, or can be used to obtain the raw moments of the distribution, hence its name, the moment generating function. And so in particular, it can be shown, and it's fairly straightforward to show, at least for discrete random variables, that the kth raw moment, the expected value of x to the kth power, is given by the kth derivative of the moment generating function evaluated at t equal to 0. Well, so this is useful because it's quite often much easier to differentiate functions than it is to integrate functions. And so in many cases, it's going to be easier. Well, in many cases, distributions that we're working with are going to have moment generating functions that are fairly straightforward to differentiate. And so when that's the case, we can find these raw moments by differentiating the moment generating function for the distribution and then evaluating those derivatives at 0 instead of integrating x to the kth power times the PDF. Now, the other reason that the moment generating function is useful is that when it exists, the moment generating function is associated with one and only one distribution. Right? So there's a one-to-one relationship between distributions and their moment generating functions. Now, this is helpful when trying to find the distribution of a function of a random variable. In some cases, it's easier to find the moment-generating function of a transformed random variable than it is to find the transformed random variable's PDF or CDF. So in other words, what you're going to find is that in mathematical statistics, theoretical statistics, we often have to calculate functions of random variables or transform random variables. And it's going to be useful, if not necessary, to find the distributions of those random variables. All right. Now, finding distributions of random variables can be a very difficult, time-consuming task. And in fact, standard statistical theory classes at the graduate level, the classes that span an entire year, spend quite a bit of time in the chapter that deals with finding distributions of functions of random variables. So this is a very important topic, and as it turns out, one of the techniques for finding the distribution of a function of a random variable is to try to find the moment-generating function for that transformed random variable. If we can do that, and if we can recognize the resulting moment-generating function as being the moment-generating function associated with some distribution, then we can conclude that the transformed random variable has that particular distribution. So there are two uses for the moment-generating function. First is to use it to generate the raw moments. And the other use, and this may be even more important from a theoretical standpoint, is for, in some cases, it allows us to identify the distribution of a transformed random variable. All right, so that is the end of the examples and the material covering expectations. The next topic is going to be multivariate random variables and their distributions, but that's going to take a little bit of time to get through, and so we're not going to do that in this lecture video. We'll do it in the next video.